Hi, my name is Charles Matlock, and I am presenting my research on the change in charge density in aluminum when it is strained. Currently, there's not much understanding into what the relationship between charge density and mechanical properties of solid-state materials is, and this research aims to better understand how the charge density changes in single crystal aluminum when it is strained to hopefully gain a better understanding of that relationship. To do that, I analyzed varying cluster sizes of aluminum atoms and exhibited them to varying levels of strain using density functional theory calculations. These clusters range from 19 to 79 atoms, and these strains range from negative 5% to positive 5% strain. To actually determine how the charge density changed in the aluminum, I used molecular orbital theory and group theory to see how the energetic percent contribution of the central atom's p orbitals to the total orbital energy changed with each level of strain. The aluminum starts with an octahedral symmetry, but when it is strained in the T2G direction, some of that symmetry is lost. The new symmetry that results from that is a D2H symmetry, which means that the p orbitals from the central atom are no longer triply degenerate. They no longer share the same energy and are instead non-degenerate. So they all have unique energies. And this means that they're singly degenerate, and that means that their energetic contribution to the system as a whole is different. Thus, the symmetry transforms from Tu to Bu, from triply to singly degenerate. And I examined the percent contribution of each of the Bu orbitals just below the Fermi energy. The results for each of the different size clusters were plotted as seen in Figure 4, comparing the percent contribution to the level of strain. Figure 4 shows the results from the 2-coordination shell cluster and the 5-coordination shell cluster, and it is clear that in the 2-coordination shell cluster, which has 19 atoms, the p orbitals of the central atom are much more affected by the strain than those in the 5-coordination shell cluster, particularly at lower strains. This shows that the charge density is moving, likely to stabilize that structure, and that the central atom is less affected by strain energetically when there are more atoms present. In the future, a much more energetically rigorous approach will be utilized with the molecular theory group in regard to the charge density motion, and the relationship between charge density and mechanical properties of materials will hopefully be better understood. Thank you.